Hello everyone, I am Praveen Kumar from BTech IT. RECode 2 event by Coding Club of PhD College of Technology have given two problem statements. In this session, we will look into uh, approach, algorithm, and the optimal solution for the two problems. Let's see the problem statement 1. A zero-indexed 2D integer array grid of size m cross n is given. Each cell has three values 0, 1 or 2. 0 represent the grass, 1 represent the fire, and 2 represent a wall. The person can and the fire cannot pass through the wall. The person is situated in the top left cell, which is the index 0, 0. The person wanted to go to the safe house, which is located at the index m-1, n-1. Every minute, you may move to the adjacent grass cell. The fire cell may spread the fire to the adjacent cells. We have to return the maximum number of minutes that we can stay in the initial position before moving, while still we can safely reach the safe house. If that is impossible, return -1. If the person can wait in the initial position regardless of the number of minutes, return 10 power 9. Let's see an example. Here is the grid. Here 0 represents the grass, 1 represents fire, 2 represents the wall. The person is situated here at index 0, 0. The person want to move to the safe house, which is here, bottom right corner, row -1, column -1. Let's see another example with better visualization. Consider this is the grid given. The person is here and the person want to move to the safe house. These are the walls and these two are fire. Each minute the fire will spread fire to the adjacent cells. This fire will spread to this cell and this cell, and this fire will spread to this cell. Let's see, if we start from time is equal to 0, can we move to the safe house? At time is equal to 0, the person is at the initial position. When the person moves here, the spread cell will spread the fire to the adjacent cells. At the next move, the person can either move to here or here. This fire cell will spread fire to here and here. This fire cell will spread to the adjacent cell, and this fire cell will spread. At next move, this person can move here. This file cell will move here. This file cell will move here. At the next move, the person moves here. This cell will spread fire here and here. This next the person will move here. This fire cell will fire this cell. The person moves here. This fire cell will be here. The person moves here. This cell spreads here. Next the person moves here. This cell will be fired. Next the person moves here. The cell will be fired. Finally, the person will reach the safe house. Now let's see, if time is equal to 1, we can reach the safe house. We are waiting for 1 minute in the same position. At the time, the fire cell will spread the fire to the adjacent cells. At time is equal to 1, this cell will spread the fire to these cells. At the next time, the person will move here. The spread cell spread the fire here and here. At the next time, the person can move either here or here. The spread cell spreads fire to these cells. At the next move, this fire cell will spread fire to here and here. At the next move, this cell can move to here. At the next move, the spread cell grabs fire here. At the next move, this is fired. At the next move, the person also moves to here. These cells are fired. At the next move, this cell is fired. At the next move, this cell is fired. At the next move, the person can either move here or here. This is fired. The person reached the safe house. Let's see at time is equal to 2 whether the person can reach the safe house or not. At time is equal to 2, at time is equal to 1, this fire cell will fire these cells. At time is equal to 2, this fire cell will spread the fire here and here. This fire cell will spread fire here. The person is still at the initial position. Now let's move to the safe house. At the first move, this fire cell will spread here. This fire cell will spread here. At the next move, this fire cell will spread the fire here and this will spread here. At the next move, this fire cell will be spreaded. At the next move, the person can either move here or here. The fire cell will be here. At the next cell, this cell will be fired. At the next move, this cell and this cell will be fired. At the next move, this cell will be fired. At the next move, this cell will be fired. At the next move, this fire cell spreads the fire to the adjacent cell. At the next move, the person moves here or the safe house. This cell will be fired. At time is equal to 2, the person reaches the safe house without getting fired. Let's see at time is equal to 3, can we reach the destination? At time 1, this will be fired. At time 2, these cells will be fired. At time 3, this cell and this cell will be fired. The person is still in the initial position. Now let's move to the destination. At the first move, this fire cell will move to here. This fire cell will spread fire here. At the next move, this fire cell will fire here. At the next move, the fire will get here. At the next move, this fire cell will move here. At the next move, the fire will spread here or here. At the next move, this is catched. At the next move, this fire will get catched. At the next move, this is fired. At the next move, this is fired. At the next move, this cell is fired. Finally, we reached the destination. So at time is equal to 3, we can reach the destination. Let's see at time is equal to 4, can we reach the destination? At time is equal to 4, this is time is equal to 1, this is time is equal to 2, this is time is equal to 4, and at time is equal to, now let's move. At time is equal to 4, this cell will spread the fire to this cell will spread the fire to here. Now move to the destination. The person will move to this position. This fire will spread the fire to the person. So the person cannot move to the destination if we start at time 4. So the maximum number of minutes we can stay in the initial position is 3. This is only given here. Until time is equal to 3, we can stay in the initial position and then we can move to the destination without fire. If time is equal to 4, we will caught in fire and we cannot reach the destination. So after 1 minute, the fire will move here, and after each minute, we will move to the safe house without getting fire. In this second example, if we move either in this cell or this cell, we will catch in fire and we can never reach the safe house. So we have to return -1. Here the maximum minutes is 3. Let's see the approach to solve this problem. Here left is taken as 0 and right is 10 power 9. Because we are using the binary search technique to solve this problem, I will tell you this later. R is the number of rows. Here it is 5 and C is the number of columns 7. I am taking in INF which is infinity as 10 power 20. Let's create a double-ended queue fires and distance matrix of size 5 cross 7 with all are filled with INF infinity, which is 10 power 20. For each, I have written it as INF itself. Each cell contains infinity value, which is 10 power 20. And we have directions. At a particular position, we can either move to the top, left, or right, or bottom. So these are the coordinates to move to the either of the positions. First of all, we take 2 loops and mark the distance. This is the distance matrix. Distance matrix has 0 where the grid cell contains 1. In each position where the grid matrix contains 1, we update the distance matrix as 0 because the cell is at the 0th time. Here 1 represents fire. At the position of distance, we mark it as 0. And at this position also, we mark it as 0. These are already fired. At time is equal to 0, these cells are fired. Next, now we are finding the number of time taken to spread the fire to each cell. At time is equal to 0, these cells are fired. At times, let's find the number of minutes taken by fire cell to spread to all the adjacent cells. Initially, the fire cell is here and here. At the time 1, the fire cell will spread to here, which is grass, and here this is a wall, and the fire cannot spread. This fire cell will spread to this cell, and this is a wall. At time is equal to 2, this fire cell will spread to this at time 2, and this fire cell will spread to here, and this fire cell will spread to here, which is not wall. This is a wall and it cannot spread. This is also a wall. Time is equal to 3. This is 2. Time is equal to 3. This fire cell is get fired, and this cell will spread to this cell, and so on. Like this, if we find the number of time taken to spread the fire using BFS, we will find all the grass cell to reach the fire. This is the final matrix, which if we take the 0, 0 cell, 6 minutes is taken to reach the fire. The INF represents the wall cell which the fire cannot spread. This is the safe off method, which returns if the person can reach safely to the safe house without getting fired at the given time. This accepts an argument time. At the given time, can the person reach the safe house? We have here W-ended QP and visited matrix to check whether the cell is already visited or not. Initially, it is all cells are initialized with 0. At the given time, if the person starts at time greater than or equal to the fire time, the person will get fired. So he cannot reach the destination. If the time is 7 and he wants to reach the destination, the first cell already gets fired in 6, so he cannot reach the destination. If the time is 0, let's take time is equal to 0. At 0, 0 greater than or less than or equal to 6, which is the time taken for the fire to reach the first cell. We append the 0, 0 index and the given time at the W-ended QP. Now let's run a loop until the Q is not empty. We pop the direction x, y and the distance d. We move to every directions. Nx, ny stores the new positions of x and y. If we start at 0, 0, directions contain 0, 1, 1, 0, minus 1, 0, 0, minus 1. We can move either to the right, left, top or bottom. If the new position is within the matrix and the cell is not visited and it is not a wall, and also the time is less than the time taken for the fire to reach the cell, we append the cell to the queue and mark it as visited. Inside within this, if the new cell is r minus 1 and ny equal to c minus 1, which is the home cell. If we reach the safe house, we return true. Or we reach the safe house at the same time the fire will reach the safe house, it is considered as safely reaching the house, and also we return true. Else if we cannot reach the safe house, we return false. Here we have used left and right because of the binary search. Here, if we start from the time 0 to 10 power 9, it will lead to the complexity of O of 10 power 9, which is very high. So for reducing the time complexity, we use binary search. Left initialized with 0 and right initialized with 10 power 9. At the first time, middle equal to this value, which is left plus right plus 1 divided by 2. Then check if the given value is safe, if we can reach at the given value. If we can't reach, then middle will the values after the middle cannot be reached. So we are making right is equal to middle value minus 1. Else if we can reach the position, we make left is equal to middle. We will reach all the values from the 0 to left value. Finally, if left is equal to 0, it is not checking value 0. So if the safe of 0 is true, return 0, else return minus 1. That's all. Let's see the time complexity of safe method. It contains a while loop, which is a queue, and within it has a for loop. The for loop runs for 4 times which is the directions, and the while loop, which is the double-ended queue, runs for row times columns, which is the total size of the grid. So the time complexity is O of R into C. Let's see the time complexity of binary search. The range is from 0 to 10 power 9. So the time complexity is O of log U, where U ranges up to 10 power 9. So the overall time complexity is O of log U into R times C. So the output for the second problem is 3. We have seen in the example. Let's see the problem statement 2. You are given an integer array coins, which represents coins of different denominations and an integer amount. The coin is a list that contains the different types of coins and an integer value amount that contains the total sum. We have to return the fewest number of coins that we can make up the sum of the amount. If we cannot make the sum of the amount by the given coins, we have to return -1. These are the examples. Let's see the first example. In first example, the coins are 1, 2, and 5, and we have to make the amount 11. There are many approaches. Let's see. Basically, we can sum up to 11 with 11 number of ones. We can add 1 plus 1 plus up to 11 1. We can sum up to 11, or 5 2 plus 1 is equal to 11, and 2 times 5 plus 1 is equal to 11. But we have to find the minimum number of coins. So the minimum number of coins will be 3. So how to solve this using coding? We can use brute force, which is we find the many combination of these three values, this 1 with 2 5 or 2 with 1 5. Many of the combination will give up to the sum, but this will take up many complexity. Using regression, we can solve this problem. It can give the result, but it will take much more time complexity and space complexity. Let's see the greedy approach. In greedy approach, we take the largest value 5 and subtract from the amount. The remainder is 6. To make 6, we need 3 2s. The greedy approach may or may not give the total amount. So we use dynamic programming. Let's see the solution. I have used a tabulation method of dynamic programming for solving this problem. Initially, I initialize the minimum coins as first index with 0 and all other index up to index total plus 1 as INF to represent infinity. Let's solve this problem. The index values are taken as amount. The value below, which is 0 INF, or the number of coins required to make the sum amount. These are the amounts and these are the number of coins to make the sum amount. If we take 0, we need 0 coins to make the sum 0. If we take 1, we need 1 coin, which is 1. We check what are the values that are less than or equal to the amount 1. In these coins, 1 is the only amount that is less than or equal to 1. So 1 coin, 1 rupees coin is required to make the sum 1. If we take 2, we check what are the values that is less than or equal to 2. 5 is greater than 2, 2 is equal to 2, and 1 is less than 2. So we have 2 and 1 that is less than or equal to 2. So if we take 2, 1 coin is required to make the sum 2 and the remainder is 0. Next, if we take 3, 2 and 1 are less than 3. If we take the coin 1, 2, 1 coin which is 2, the remainder is 1. Next, we find how many number of coins is needed to sum the take the value 1. For the value 1, 1 coin is required. So the total coin is 2. Let's erase it. And for the value 4, 2 and 1 are less than 4. Let's take 2. 1, 2 coin is needed to 2. And the remainder is 2. The number of coins that is needed to make the value 2 is see in the index 2, it is 1. So extra 1 coin. So total of 2 coins is required to make the sum 4. 2 times 2 is 4. Let's see 5. Before that we delete this. Let's see 5. The 5, 2 and 1 are less than or equal to 5. If we take 5, 1 coin is required to make the sum 5. Let's take 6. 5, 2 and 1 are less than or equal to 6. If we make the sum, want to make the sum 6, 1 5 coin is required. 1 5 coin is required. Remainder 1. If you want to then check a number of coins required to make the sum 1. At 1, we have only 1 coin. 1 coin is required to make the sum 1. So we update the 6 as 2. 2 coins are required. 5 plus 1 equal to 6. Let's see 7. To make 5, 2 and 1 are less than 7. If we take 5, 1 5 coin is required. The remainder is 2. To make the sum 2, 1 coin is required. See here, to make the sum 2, 1 is required. So 1 coin is required. To make the sum 7, total of 2 coins are required. 5 plus 2 is 7. Let's see 8. 5, 2 and 1 are less than 8. We take the highest value 5. If we take one value 5, the remainder is 3. If we want the number of coins required to make the sum 3 is 2. So plus 2 coins. Total of 3 coins are required to make the sum 8. If you want to make the sum 9, 1 5 rupees coin is required, plus the remainder is 4. If you want number of coins required to make the sum 4, here 2 coins are required. So plus 2. The total sum is 3. You want 1 5 coin and 2 coin to make the sum 9. If you want to make the sum 10, we take 1 5 rupees coin. The remainder is 5. The number of coins required to make the sum 5 is here 1. So 1 plus 1 is 2. 2 times 5 gives 10. Next we want to make the sum 11. We take 1 5 coin plus the remainder is 6. The number of coins required to make the sum 6 is 2, which is here. So 1 plus 2 is 3. 5 plus 5 plus 1 gives 11. So the number of coins required to make the sum 11 is 3. Let's see the time complexity of the problem. It has 2 loops. The one for loop is nested inside the another for loop. The outer for loop runs for 1 to total amount plus 1, which we consider as 1. N. The nested for loop runs the number of coins in the coins list, which is C. So the overall complexity is O of M times C. This is the final output. I have given the coins list as 1, 2, and 5, and the total amount is 11. This is the intermediate process that occurs in the array during finding the total sum. This is what I have written in the previous slide. So the last index value is the total sum, minimum number of coins required to make the total sum. If this last value is infinity, we cannot find the coins that will make to the sum. If it exists, this is the minimum number of coins. Here it is 3. Thank you.